Hello everyone, good afternoon. My name is Sourabh B.Ghode and I am a PhD student. This is my fifth semester, and today I am going to present one of my published review paper. Name is 3D multi-state memory structure for neuromorphic in-memory computing. So before start my review study, I will give some publication details. So this paper is published in Material Science and Engineering R report. So worldwide impact factor is 36.8, and this is the most good journal in material science and engineering field. So today I will present my work, like from the introduction of 3D memory to the application, like how it will limitations, then fabrication techniques, then device challenges, parameters, all things I will explain. So in this slide I will tell about the evolution of memory technology, like from the theoretical concept in 1971 to the 3D neuromorphic system. Like today, what is the why researchers are going through the doing study for the memory field. So first I will in this slide I will explain about the what is the 3D memory. So 3D memory used 3D memory are used vertical stacked resistive switching behavior layers. They overcome the density limitations of the planar 2D architecture. So vertical integration enables the ultra high device density and suitable for the compact memory and neuromorphic hardware. Also supporting for the in-memory computing with the low power consumption, reduce data transfer latency and energy loss. Also 3D memory enable the multi-state like analog resistive switching behavior. This is the useful for the synaptic weight representation in AI system. Also 3D memory can mimic biological synaptic behavior and plasticity also. Also it support learning and weight modulation function. Also 3D memory have common material include metal oxides and phase change materials. The fabrication often the fabricated using low temperature deposition method. So in this slide I will explain about the reimagining all AI hardwares including GPU, TPU, NPU, and why 3D memory can take all of kind of AI hardware place. So in TPU, the mostly matrix multiplication optimized TPU is the matrix multiplication optimized the hardware. It can detected the tensor processing for the AI workload and improve the computational efficiency compared to the GPU. In MPU case, neural processing unit connect with the processing engines, parallel data programmation and activation pipeline. Also, this is designed for the efficient AI and neuromorphic operations. And in 3D memory crossbar array case, like 3D memory is vertically stacked memory synaptic arrays. It supports the analog weight storage and the in-memory computing. Also, it can mimic the biological synaptic behavior for the neuromorphic. So in this slide we will discuss about the what is the difference between 2D memory and 3D memory architecture. So mainly 2D memory are arranged in the planar classbar configuration, where resistive switching devices are fabricated on the single layer. Each memory and in 2D memory each memory is accessed through the horizontal word lines and vertical bit lines, limiting the scalability to the chip surface area. Also they exhibit the binary or limited multi-state resistance switching and suitable for the basic non-volatile memory and simple neuromorphic applications. And in the case of 3D memory stir, 3D memory stir utilize the vertical stacking of multiple memory stew layers, dramatically increase the integration density behind the planar limit. Also, it can like vertical architecture enable the high and massive synaptic connectivity, closely reassembling the biological neuron networks. Also, they can support the multi-state such as analog, conductance, and modulations, enabling the precise synaptic weight representation for the neuromorphic computing. So, in this slide, we will discuss about the which material is suitable for the 3D memory stir. So, in 3D memory stir case, like transistor metal oxides such as HFO2, TiO2 are the most widely used memory stew materials due to their stable resistive switching and CMOS compatibility and scalability. Also, in 3D memory stir nowadays, phase change and electrochemical materials like for example GST alloys or copper based material enables the multi-state switching and low power operations, making them the attractive for the neuromorphic application. And these materials can these materials are emerging material including 2D material, heterostructure and perovskite materials, porous materials, porous composite layers offer improve the ionic transport and thermal management and device uniformity. But in 3D for fabrication for 3D memory 3D memory stir have some challenges like device variability across the stack layers affect the synaptic weight accuracy. Also, thermal management issue arise due to the vertical stacking and vertical stacking and high density. Also, sneak path current is big issue, like sneak path currents and crosstalk degrade the read write reliability. And fabrication complexity limits yield the large scale integration and endurance and retention degradation under the repeated analog switching. So, to overcome these challenges, there are some good fabrication strategies we discussed in our review paper. So, first is low temperature deposition technique, like for example atomic layer deposition, sputtering, enable the multi-layer vertical stacking. Also, vertical crossbar and monolithic 3D integration improve the density while the minimizing the footprint. Also, selector memory stir integration suppress the sneak path current and dense array. And self alignment patterning method, it can like in this method like nanoprinting, lithography support the scalable fabrication. And material and interface engineering improves the uniformity and layer to layer reliability. So from now we will discuss the the proposed memory structure based on neuromorphic device for in memory computing. So first we will discuss about the 3D ferroelectric memory stir. The 3D ferroelectric memory stir can provide high density and low power consumption and low power neuromorphic computing. Also, ferroelectric switching enables the state analog conductance modulations for the synaptic emulation. So in ferroelectric memory stir we can use like HFO2 based ferroelectric materials that can offer the CMOS compatibility and multi-level memory states. Also in ferroelectric memory stir, vertical stacking architecture significantly improve the memory integration and high density memory. So in this figure they proposed like so many like FTJ based ferroelectric memory stir. It can achieve 96.84 minutes recognition accuracy with the ferroelectric memory stir. So for the future study we can fabricate the 3D ferroelectric memory stir for the high density and low power consumption neuromorphic computing. So another memory stir is flexible 3D memory stir. The flexible 3D memory stir combine mechanical flexibility and high density neuromorphic integration. And 3D memory stir is suitable for variable electronics, artificial skin or robotics and healthcare monitoring system. So flexible memory stir can bend, stretch, and conform the curve surface. Also in 3D memory stir case, like HFAL-O2 based stacked memory stir maintain the stable synaptic behavior under the bending state. So in figure you can see the three layer PT HFAL-O2 and 10 crossbar array shows the LTP and LTD characteristics, then with minimal electrical degradation and observed during the flat and bend operations. Also vertically stacked synaptic array can support STDP, LTP and LTD and analog weight tunneling. So next one is 3D optoelectric memory stir. So this memory stir can combine the sensing, memory and processing in the single platform. Their device can respond to both optical and electrical stimuli, and this 3D optoelectric memory stir can suitable for vision and multisensory AI system. So in this figure you can see vertically stacked 3D architecture provide the high synaptic density and parallel processing. And in this figure you can see M3D architecture reduce the latency, energy consumption and data transfer overhead. Also image sensor, analog CM and CMOS logic are integrated into the structure. Next one is 3D vertical memory stir crossbar array. This memory stir can enable the high density neuromorphic computing. These architectures support the in-memory computing and the analog parallel processing. Multiple memory stir layer are vertically attached to the interface integration density. So each crossbar cross point memory stir act as an artificial synapse with the tunable conductance. So this type of memory stir also we can this type of structure is very like good for the next artificial intelligence. And last one is the monolithic 3D integration. This type of memory stir enable the compact high density neuromorphic hardware. Also multiple function layers are sequentially fabricated on the single chip. This architecture reduce the interfacial length, latency and power consumption. It overcomes the non-human bottleneck by the collating memory and computing. So this system achieved the 18 lower energy delay product than the conventional 2D memory stir system, and this stacking supports by high speed memory and local this like high memory computing. So at the last we here you can in this slide you can see the SWOT analysis. So the strength, weakness, opportunity, next opportunity, and what is the threats. So lastly I will this is the conclusion slide. So 3D memory stir architecture overcome the scalability limit and conventional 2D memory stir system through the vertical integration. This type of multi-state and analog switching enable the efficient synaptic weight represent for the neuromorphic computing. In memory computing capability significantly reduce energy consumption and latency. Despite the challenges and advantage, the in material fabrication and architecture design continue to improve performance and performance. Also 3D memory stir can represent the promising pathway towards the brain inspired high density and energy efficient AI hardware, and high parallelism and massive connectivity enable the faster learning and interface operations. So this research continued on the variability control and the thermal management is essential for large scale neuromorphic development. Thank you.